Today we want to think about the derivative a little bit more. We spent a lot of time finding some derivatives because that gives us some nice mechanical skills that we can work on. But today we want to think about what the derivative is telling us. Now we know that the derivative is telling us the slope of the line tangent to a function at a given point. We've interpreted the derivative as the instantaneous rate of change of a function at a point. So what the derivative is telling us is the direction of the function. We want to think of the derivative telling us the direction of the function. So we want to be more specific about this direction of the function business. Now, when we're dealing with a function of just one variable, direction is just going to be up or down. So if we're thinking of a function of just one variable, all we have in terms of direction is like an up or down as we read from left to right. And that's what the slope is telling us. As x increases by 1, what happens to y? Y either goes up or it goes down, or it could do like neither. It could split the difference and do neither. So y is either going up or going down, or it could be flat. So the function could be going up, or it could be going down, or it could be going flat. Up or down and neither. As x goes to the right. We read this, we are reading derivative like we're reading slope. What's happening as x increases? That indicates the direction of the function. This is just what slope is telling us. The difference now is that instead of just having a line with just one direction, the direction is continuously changing. The direction is different at all these different places. So if we have a function, I'm going to have a function that goes up, down, and then up again. I'm going to draw a picture of a function that goes up and then down and then up again. Where the x-axis is not really important. So there are two places that we can see on this graph where the function is flat. So there are two places on this graph where we can see that the function is flat. Let's give them names. Clever names like x1 and x2. I should joke that I would name my kids just after letters of the alphabet, like A, B, and C, but that's not true at all. I would definitely just use subscripts. Kid sub 1, kid sub 2. Well, how many are you going to have? Well, N. Where N is a non-negative integer. But then the reality is, and also a non-positive integer. So notice that the function is flat at x1 and x2. The function is neither increasing nor decreasing. The function in this case, in both these cases, is turning around, changing direction. The thing we want to notice is that the function is flat at x1 and x2. F of x is flat . So first notice that f of x is flat at x1 and x2. So what is the slope of the tangent line at x1 and x2? What's the slope of a flat horizontal line? Slope of a flat line. 0. So since the function is flat at x1 and x2, that means the slope of the tangent line is 0 at x1 and x2. The slope of the tangent line is 0 at x1 and x2. Slope of the tangent line is determined by derivative. So we know we can put those two things together because we're sophisticated calculus students. So that tells us that f prime of x1 and f prime of x2 is equal to 0. So the function is flat at x1 and x2. The slope of the tangent line is 0 at x1 and x2 because the function is flat. So that means that the derivative is 0 at x1 and x2. When the derivative is 0, the function is flat. Note that before x1, the values of the function are going up. The values of the function are increasing. Before x1, the function is increasing. So in this region here, so for x less than x1, the values of f of x are increasing. So we'll just say f of x is increasing. And because we know that x is the variable in play, we're just going to say f is increasing. So for x less than x1, f is increasing. The same is true for x greater than x2. So before x1 and after x2, when we look at the values of the function, reading from left to right, we see the values of the function going up. So for x less than x1 and x greater than x2, f is increasing. That's how we're describing the direction. The only directions we have choice for are up and down, and y is going up on those intervals. If I stick a tangent line at any point on those intervals, notice that the slope of the tangent line is going to be positive. It's going to be pretty steep down here, and it's going to flatten out. But all the points before x1, the slope of the tangent line is positive. If I pick this point, draw a tangent line, slope is positive. Even at this point, it's less positive, but it's still positive. This point after x2, slope is positive. That class sounds so much more fun than ours. So what we want to associate is increasing with positive slope. And since slope is derivative, we're going to associate increasing function with positive derivative. So we'll see, notice that the slope of the tangent line is positive. The slope of the tangent line is positive. And so f prime is positive. When f prime is positive, the function is increasing. When the function is increasing, f prime is positive. The first derivative is positive, the function is increasing. When the function is increasing, the first derivative is positive. What am I going to write next? That was the tricky part. You didn't know I was going to misspell slope. So we noticed that at the point x1 and x2, we saw that the function was flat. What that meant was that the slope of the tangent line is 0 at x1 and x2. That means the first derivative at x1 and x2 is equal to 0. Before x1 and after x2, we saw that the function was increasing. We noted that we decided that is associated with the slope of the tangent line being positive. And so f prime, the first derivative, was positive. So what am I going to write in this section? What's happening between x1 and x2? F is decreasing. So the slope of the tangent line is what? Negative. And so f prime is negative. The sign of the first derivative is telling you the direction of the function. The sign of the first derivative is telling you the direction of the function. The sign of the first derivative tells you the direction of the function. If the first derivative is positive, the function is increasing. If the first derivative is 0, then the function is flat. If the first derivative is negative, then the function is decreasing. Any questions? Sign of the first derivative tells you the direction of the function. The direction of the function will tell you the sign of the first derivative. It will work both ways. So if f direction of the function tells you the sign of the first derivative. The sign of the first derivative tells you the direction of the function. If you know one, then you know the other. Any questions? Of course not. There's the TLDR right there. So far. Actually, that's too much TLDR. This line right here. Sign of the derivative tells you directly the function. Let's look at the function and see what the derivative tells us. I was trying to give myself some zeros, but then it messed up my maximum and my minimum points. So I just went with the weirdo zeros. So we'll just have to cope. We know how to complete the square, so we'll be fine finding the zeros if we need to. All right. So pretend that we didn't see that. We knew that that's what this function looks like. It's a polynomial function. It's third degree. It's odd degree. It has a positive leading coefficient. So we know a lot about this function already. In particular, we know what its shape is going to be. So the things that we notice about this function. We have a positive leading coefficient. We have a positive leading coefficient, the 1/3. So we know that as x goes to infinity, this function goes to infinity. That tells us what the graph is doing as x goes to the right. Right. We notice that the degree is odd. So whatever the right side is doing, the left side is doing the opposite. So the left side is going to do the opposite of what the right side is doing. Since we have fancy calculus notation about things, we can phrase this in terms of limits the same way. We could say the limit as x goes towards negative infinity. I spelled negative infinity wrong. And since the degree is 3, this graph can make either 2 or 0 turns. Since the degree of our polynomial is 3, this graph will make either 2 turns or 0 turns. We can't make an odd number of turns because the ends have to go in opposite directions. We can't have ends going in the opposite directions and make one change of direction. Because there has to be at least 0 changes of direction. Starts going up, keeps going up. Or if it makes one change of direction, it has to make another change of direction. Otherwise, the ends will not be going in opposite directions. Kind of a bad way to phrase it. Doesn't matter. So we either make 2 turns. So we know that one end is going up because of the positive leading coefficient. We know since it's odd degree, the other end is doing the opposite. So as x goes to negative infinity, it's headed down. So one thing that could happen is that we make two turns. Turn around here, turn around there. One thing that could happen is two turns. Another thing that could happen is that we make 0 turns. So we know that if this end is doing this, and this end is doing this. Another way that this could happen is we make 0 turns. Notice that the graph bends. Bending is fine. It's not changing direction. The graph is always increasing. A turn is a full-on change in direction. The other way we can make 0 turns is the graph can flatten out, take a little rest. So to make 0 turns, that means we could either have one flat point where it's increasing, goes flat, and then just keeps on increasing, or never flattens out, just slows down and then keeps going up. These are the two things that ways we can have 0 turns. No flat point, one flat point. Or we can make 2 turns, in which case we have 2 flat points. When I say turns, I don't mean bends, I mean changes in direction, changes from increasing to decreasing. From increasing to decreasing, or from decreasing to increasing. These are all the things that we know just by looking at the leading term of our polynomial. Leading coefficient is positive, degree is odd, degree is 3, so 2 turns, or 0 turns. All from the leading coefficients. We also notice that it's since an odd degree, speaking of this is just like the turns and the shape. Other things that we know, since it's odd degree, it must have at least one real 0. It has to have one real 0. Convenient that we could see what it is. That's how you make your life easy. Make 0 one of the zeros. There it is. But we knew it had to have at least one real 0 because it's odd degree. We're going up on this side and down on this side. We have to pass the x-axis once. We can't jump over it because the function is continuous. Look at all the calculus stuff that is supporting what we already know. Some DVD bonus material. The function changes sign one time. The first term is positive, the second term is negative, the third term is negative. So there's one change in sign. So there's going to be one positive real 0. So if we start looking for a real 0, there's one positive real 0. If we look at f of negative x, that's going to be a negative x cubed, negative x squared, positive 3x. That means it's going to be one negative 0. So now we have a lot of information. So if you want the DVD bonus material, So f of x has one change in sign. We go from positive to negative to negative. There's one change. That means f of x has one positive real zero. That's nice, solid information. Furthermore, f of negative x which will be negative 1/3 x cubed minus x squared plus 3x, also has one change in sign. Therefore, f has one negative real zero. The reason this is useful information because Descartes' rule of signs, which everybody remembers from pre-calc, right? No, of course not. It was in algebra. I'm just kidding. Of course not. We never talk about that. We have graphing calculators now. But Descartes' rule of signs says count the number of times the sign changes in your polynomial with real coefficients. The number of positive real zeros will be that number or less than that by an even number. That's what makes this useful. If we had two changes in sign, there could be 2 or 0 positive real zeros. But with one change in sign, there's going to be 1 or 1. There has to be 1. So that's useful information. So now we know all about this function. We know exactly what's happening without thinking about it any further. It has to be this two-term version. It has to be, because we know that 0 is one of the zeros because of the way what I chose. I made every term a factor of every term. I have a common factor of x, easy to see. Another thing is what could happen. The other two could either be 2 real zeros or a pair of complex conjugates. There's 1 real zero for sure because it's third degree and we can see what it is. It's a third degree polynomial. There are 2 left. Those 2 other zeros can either be 2 real zeros or complex conjugates. Now we know what's happening. It must be 2 real zeros because there's 1 positive one and 1 negative one. No analysis, no calculations. We just look at what's going on. Just read it. That's called Descartes' rule of signs. That's your DVD bonus material for today. Yes. We just count the number of sign changes. It starts off positive, then negative, then negative. It changed signs 1 time. So Descartes' rule of signs says there's 1 positive real zero. That's your obscure math knowledge for the day. Most people, has anybody ever heard of Descartes' rule of signs before? Because you have graphing calculators, right? Like, oh, just graph it. Is that a super useful result? I don't know, not really. It depends on what you're trying to do. It always depends. I don't think I was taught, this is an old enough result that I don't think I was taught this in any kind of serious capacity. It was mentioned to me just like I mentioned it to you. It usually falls in the category of no one's got time for that. It's like, well, it's an algebra thing. Should it be in an algebra class? And everyone's like, oh, no, it should not. This stuff should be from your algebra class. Or your pre-calculus class. Which is just your third algebra class. I don't know if you recognize it. There's like an elementary algebra, there's an intermediate algebra, and you're like, oh, where's the next algebra class? Why is there one called intermediate if that's the last algebra class you take? Do you ever notice that? When sodas were first getting bigger at the theater, it would used to be like small, medium, large. They're like, oh, we don't make the small anymore. The smallest one you can get is medium. It's like, oh, motherfucker, you do not know what the word medium means. Just because small is bigger than it used to be, it's still the smallest one. And then Starbucks is like, oh, no, we like that. Tall, grande, and venti. I go, what the fuck is that? The shortest cup is tall. I mean, this is like, I realize that this is like basic bitch observational comedy shit, but what the fuck, man? Just go like 20, then whatever, like 16, and then like 12. I don't know why two have to have words, and then the last one can be like the number. You know what I mean? It kind of reminds me of when you see like there's a kind of a common joke where we measure anything, we measure using anything but the metric system, right? As if using the metric system would be any good whatsoever. As if using the metric system for in like headlines and shit like that would be any good whatsoever. If I told you that a 5-meter sinkhole opened up in the road, can you picture it? How big is 5 meters? Now, if I told you a hole the size of a minivan opened up, a sinkhole the size of a minivan opened up in the road, can you picture the hole? Yeah, because you picture a minivan and you put it in the fucking hole. When I say minivan, that defines a particular size. It evokes size in your mind way better than 5 meters does. From here to there, how many cars could we park? Parallel. How many parking spots would you put in this space? 2? 2 is reasonable. What if the people that were parking here were really fucking good at it? Probably 3, right? Depends on the car, right? If they're really good at parallel parking, but they're driving Challengers, then I don't know. 1. Car's like 80 feet long. 2 doors, 2 useful seats. Let's make the car 100 feet long. How long is your car? You can use feet if you want. I know this is America. I don't have one. You're like, oh, 0 feet. Ah, I got that one. Gotcha, bitch. If you have a car, how long is your car? Anybody else? How long is your car? What the answer is? It doesn't fucking matter how long your car is. You don't have to know a number for your car, how long it is. You don't have to know the number. I mean, if you do, then you're probably just a car nerd. But if you don't have to know the number, you just have to like drive up, see a space at an angle, by the way, through the window of your car, at an angle, under pressure, because there might be people behind you, and say, I can fit my car there. And you drive up, and you see, big enough. How long is my car? Short enough. How big is that space? Long enough. Do you know what I mean? My car is 150 inches long. Is that hard? Is that small? Ridiculously small. I drive it in. It's very short. There's only one production car that I can think of that is shorter. I don't think they make it anymore. And it's a Fiat 500. So those things are extra. Do you know what I mean? So, like when people make fun of humans for measuring things in weird ways, my favorite was like 7 washing machines. It's like, well, I can picture 7 washing machines. I've been to the fucking laundromat. I know what 7 washing machines looks like. If you told me what that distance was in meters or feet,
What's the point of that? How is that useful? If I say something is 300 feet away, what's a better measurement for that? Oh man, it's like 300 feet away. Can you picture 300 feet? Can you picture it? What would you use? A football field. You can picture yourself standing out on the football field and saying that is about 300 feet. And someone is at the other side. I'm pointing where the football field is. It's way further than 300 feet away. But that's something that you can picture, right? It's a better measurement. If you're trying to get people to picture things, it is a better measurement than any kind of distance. See what I mean? Anyway. See, they get it. Just kidding. Anyway, what we're talking about, we got cars that park themselves now, so I don't know what we worry about. Although it still bugs me when people pull in the parallel park and then like pull in forward. It's the front wheels that turn. That's why you back in. You know that? Just if you're learning to drive, you back into the spot because it's your front wheels that turn. If your car has the back wheels as the turn wheels, then you'll want to front into the spots. Anyway, that's all beside the point. Descartes' rule of signs. It has a Wikipedia entry. It's pretty cool. It's super obscure. But so we know we're in this situation because we have obscure, like hella obscure math knowledge. Let's see what happens if we analyze this with derivatives. So here's our function. F prime is 1x squared minus 2x minus 3. F prime is x squared minus 2x minus 3. We can figure out where the function is flat by setting this equal to 0 and solving. If f prime of x equals 0, we see that there are two places where the function is flat. So we see that f is flat at -1 and 3. So now we know what's going on in this function. We know that it must be this shape. It must be this 2 turns because when we looked at the derivative equals 0 had 2 solutions. So it must be that it has a flat, it's going flat here at -1 and flat here at 3. Before -1, the derivative must be positive. After between -1 and 3, the derivative is going to be negative. And after 3, the derivative is going to be positive again. If we take a look at the graph, this is the same graph that we were looking at before. That's exactly what's going on. There's the 0 of the 0 at 0. There's also the -0 and the +0. They're irrational, not surprisingly, because of our function. A third x squared minus x minus 3 does not have any rational zeros, so no surprises there. And if I drop the derivative on here, what is it? X squared minus 2x minus 3. We see that when the derivative is 0, the function is flat. When the derivative is 0, the function is flat. Before -1, the derivative is positive, and we saw the function increasing. Between -1 and 3, we see the derivative is negative because it's below the x-axis, here below the x-axis. And the function was decreasing. And then from 3 onward, after 3, the derivative is back to being positive and it will be positive forever, and the function will go back to increasing and be increasing forever. Question? We want to take what we know about functions already and incorporate derivative. The sign of the derivative tells you the direction of the function. For direction, we mean increasing, decreasing, and then neither of those, which I call flat. Any questions? How's that okay? Simple, right? We're just taking stuff that we already knew and adding to it. It only seems like a lot to remember because it's a lot to remember. And you have to remember all of it. All the time. In perfect detail. Best I can do is give you multiple chances to get things wrong. That's going to do it for today. I will see you all on tomorrow. We will use the derivative to analyze some more functions and think about more graphs. Everybody have a good day, and thanks for playing.